So finally, I am going to talk about data assimilation for estimation of local physical parameters, meaning because this is a microscopic technique, we want to obtain the local physical parameters, meaning lifetime and the transport properties of the charge carriers, and we use a data assimilation technique. So in the data assimilation, we use a diffusion decay model and combine the numerical simulation and common filter. Every step we can obtain the data and then calculate the model. They are adjusted to obtain the recovery signal. And during this process, we can obtain the lifetime and the diffusivity. So I'm going to briefly explain introduce the data assimilation. Probably this is very frequently used for the weather forecast. For example, you can obtain the cloud image every time, and also many other weather information. So every time you could obtain the data, and then you have some physical model of the signal, and it is adjusted to the data by adjusting the parameters, and then finally you could obtain the good physical model for to describe what you are observing. So in our case, data assimilation used like this. So we have information of the charge carrier distribution in a spatial direction in time, and we measure the data by the imaging here. So what we think about is the probability of when the m is obtained and n is obtained at time t equal t minus 1, and then predicted one step, and then measurement step with some reasonable noise, and to adjust the physical model to the actual measurement data, and then prediction gain. So during this process, we can obtain the physical property values too. So in the case of photoexcited charge carriers, we are interested in the mobility or conductivity, mu. And this is related by the Einstein's law, Einstein relation, so mu and d. So d is a diffusion coefficient. The difference of the photoexcited charge carriers is they have a lifetime, right? So the physical model of the photoexcited charge carriers change in time and space is controlled by the diffusion term and also the decay term. Right? So what we need to do is when we observe we could observe this kind of refractive index pattern at each local position. We applied this physical model to estimate the local parameters. So what we are doing is here, for example, at each local position at this section profile, you could obtain the time response of the signal, the refractive index change corresponding to the distribution of the charge in space, and it was gradually decaying. And then this could be modeled by the partial differential equation, as I mentioned. And then by applying the data assimilation, we could recover this kind of response for this by the data assimilation. And during the data assimilation process, we could also obtain the lifetime and the diffusion coefficient, as I mentioned. And we did a scan for all these line parts. and we could obtain the diffusion coefficient in the left and right direction, and also the inverse of lifetime K, and they could be mapped out. So you could see that as a very inhomogeneous actually, and it suppose our assumption that particulate films has many varieties of the physical parameters. So we can map out these physical properties values. And here's one of the examples for the actual TiO2 nanoparticulate film. This is the SEM image. You could see the many nanoparticles. And the transient response shows like this. It's on the logarithmic time scale, so from nanosecond to microsecond to the millisecond order. And one single step, a single response part, this rising part corresponds to the trapped electron recombination that we already assigned. And what we did is here's a TG imaging responses, right? And we could obtain the many different local responses like this. And by using the data simulation, we can obtain the lifetime mapping for this sample. And it shows a very kind of dependent on the sample position. And if you look at this lifetime mapping, and the lifetime is mapped out by the histogram, you could see like this kind of broad distribution of the lifetime. And we usually use average lifetime, in this case 0.5 500 nanosecond. But actually, the lifetime distribution extended from the 0.1 to 0.9 microsecond. So with that, here's a kind of the pictorial summary of our research. We've developed a new microscope using the pattern elimination phase microscope, and improved it with a high time resolution imaging, and also using the various informatics technique like image reconstruction by the sparsity and also the PCA, and the data simulation utilized for the physical property estimation. And by combining the measurement and the informatics, we can obtain the local carrier mapping method. So with that, here's a summary. Again, we've developed a new microscope. We are visualizing the in our case, non-radiative recombination process of for excited charge carriers, because we use a refractive index change for nanoparticulate semiconductor films. And refractive index image was obtained with a time resolution about 3 to 5 nanosecond, and the image quality was enhanced by the combination of the setup, the pattern light illumination, and also the up-to-date image recovery algorithm, and also utilize the phase physical property estimation by using the data simulation technique. And again, this one is recently published in the JCP. And with that, thank you very much for your kind attention.